Well, I haven't tried this before. Let's give this a go. Hello, INTD301. This is me in my house, talking to you in your house. I sure hope you're in your house. That's where you're supposed to be. So I wanted to talk a little bit about the exponentiation questions that you were supposed to have been doing. In particular, I would like to speak about several of my pet peeves. Let us talk about several of my pet peeves. One comes in the proof that I'm sure you did, that x to the a times x to the b is x to the a plus b, how you would explain that to a teenager. And I'm imagining that your explanation is something like x to the a is x times x times x times x, and then x to the b is x times x times x times x. So let's talk about how we talk about those things. First of all, when we say times, that's a raised dot. When we say dot, 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 those are dots on the ground. So we write it like this. There's a dot, and then that's a multiplication dot. Then there are three dots, not four dots, not two dots, not 10 dots, three dots, and there's a multiplication dot. That's how we write it. We also say A copies and B copies. We do not say x is multiplied by itself a times, because that's false. X is multiplied by itself a minus 1 times. We will now all pause while you get that. Similarly, there are b copies. It is not that x is multiplied by itself b times. That's just plain false. X is multiplied by itself b minus 1 times, and that's how you get b copies. So altogether, these are a plus b copies, and that is this, and we're good. The second, I suppose, is not really a pet peeve, but we should set on a firm foundation why z to the negative n is 1 over z to the n. I have heard people say that's by definition. It does not have to be by definition. You can infer that z to the negative n must be 1 over z to the n. Why? Because we know that z to the n times whatever z to the negative n is, whatever you decide this is, z to the n times z to the negative n has to equal z to the 0. And you know that z to the 0 is 1, and so z to the negative n must be 1 over z to the n. So we do not have to say that this is a definition. There are some people who say, well, we define z to the negative n. No, we don't define z to the negative n. We infer what z to the negative n must be based on what we know about laws of exponents. So then the third would be, why is it that if you take some real number to a rational exponent and raise that to a rational exponent, you get that real number to the product of those rational exponents? Why is that the case? We assume W1 and W2 are rational, which means that we're really doing r to the a over b to the c over d. That's really what's going on. R to the W1 to the W2 is R to the A over B to the C over D. And then we take our meaning, what is being raised to the C over D? The bth root of R to the A. So then what is that? This is the dth root of the bth root of R to the A to the C. Well, now comes the trick. Can we kick this A out? Well, what is this? This is the bth root of r times the bth root of r times the bth root of r, and so on, until there are A copies of the bth root of r. And so that does imply that we really are taking the dth root of the bth root of r, A copies of it. And that is being raised to the c power. So power to a power, that's great. Root of a root, that's great. And that is what you're looking for. That is the thing that you're looking for. So we are confident that for rational exponents, the laws of exponents hold. The proofs of the other properties are written in your textbook. This is the one that isn't. So I'm hoping that that's helpful to you. The video that follows this one in the Canvas page will be all about setting the real valued function on a firm foundation. It is just a little bit more complicated, but I think you will understand some things. Cool. Hopefully this gave you some sort of inspiration to go back and take a look at some of the questions on that worksheet, saying, oh, is that what he meant? Well, we can prove that. So I'm hoping that that goes well for you. Go back and play with those properties. You can justify those properties. I have full faith and confidence. All right, that's enough for this. Next video will follow, and it'll be about real valued functions. Thanks a lot.